Last class, we were looking at urns pulling a red ball and a white ball out of an urn. In today's class, we're starting with a monkey. And the monkey is typing two letters, S and F. So imagine a big, did I say typewriter or keyboard? Keyboard that only has the letters S and F. And the monkey is going up to it and pressing different buttons. And we're making some assumptions here. So we're supposing that the letters are independently at random. So the monkey picks a letter at random, and what they choose on one button press does not affect what they choose on a different button press. I am told that real-life monkeys do not behave like this. So a real-life monkey will find one button and press it over and over and over again. That's not what we're doing here. So this one, the monkey just does them at random, which is interesting. We're going to learn more about this independently at random. Of course, we know what independently at random means for events. That was a big topic for the midterm, but we don't know what it means yet for random variables, but we will soon. So the outcome of each letter does not affect the chances for future letters. That's a nice way to say it. Suppose also that there is some probability P for the S's, and there's some probability Q, which is 1 minus P for the F's. And the monkey types out 7 letters. So we have a document with 7 letters, and then there's 2 different events here. One is that you get 3 S's and 4 F's, and one is that you get FS, 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 FS. Let's see what you said for this one. Reveal counts. All right, so in this one, we're pretty split. Out of 57 people, just about half the people picked P to the 3, Q to the 4 with a 7 choose 3 in front, and about half the people picked P to the 3, Q to the 4 without a 7 choose 3. And then for this one, where they were all in a row, so that was the first one, it was pretty split, and the second one also pretty split. The second one is almost exactly 50-50. So that is a good sign that there is some confusion here about what is going on. This is exactly, if you can get this straight in your head, which one is which, then you will be the master of the binomial distribution. Maybe let's recall the binomial distribution. I think it's up here on the other computer right now. Let's put that up. So this is what we looked at last time. We'll give you a quick reminder, and then we'll let you vote once again. So this was what we derived last time. This formula, P of x equals n choose x, P to the x, Q to the n minus x. And then the only question is, what is this representing? So this is the probability of something, but what is the something? That is the important context that you need to answer the question. It is the probability of the random variable x being equal to lowercase x. So in other words, maybe I'll write it on the board over here. Lowercase p of x is the probability that capital X, the random number, equals lowercase x. And what is capital X? It's the probability of the number of S's, the number of successes, the number of S's. Number of S's equals x. So that is the thing to remember. This is what we derived last time. It's the number of successes. Successes can be whatever you want. As long as you have 2 categories of things, you can label one of them as the successes. For the monkey, we had S's and F's, so it's kind of not a coincidence. Okay, N's and P's, and their trials are with replacement. Okay, so that was a quick review. We're pretty split on 50-50 on the mathematize. I will open it up once more for a second round of voting to see if you can figure it out now that you've seen the review. Talk to your neighbors and see their perspective as well. Any questions or comments before we jump back into it one more time? All right, let's do it. Let's do it again. I'm going to open up a copy of the mathematize once again, where now that you have the hint, you can talk to your neighbor and see, can you figure out which of these 2 it is? Oh, I guess I will tell you these 2 are wrong. So it does involve P's and Q's. Don't vote for a P to the 7. The P to the 7s are definitely wrong. So figure out which of those 2 you think it is and vote for that. I will open it up once again by hitting this button right here. And now it is open. So go ahead and you can revote. I will give you 1 minute. Time is up. Let's see if this time with the hint, we were able to figure it out. Reveal counts. Okay, this time, pretty big majority on the first one with the 7 choose 3. 2 people are asleep. And on question 2, only 1 person is asleep on question 2. Amazing. But pretty sizable majority on the p cubed q to the 4. And that is perfectly correct. So the first one, this is the kind of binomial question. You have a sequence of these things, and you're asking the number of s's. That's the random variable we care about, the number of s's. And that one involves this binomial thing, 7 choose 3. This is also called a binomial coefficient. It's the coefficient that goes in front. On the other hand, this one, getting a specific sequence, there is no binomial coefficient. You have to get it. There's only one way it can happen. What is the chances it can happen? Well, first you have to get an f, then you have to get an s, then you have to get an f, then you have to get an s. There's only one way it can happen. And if you just count up the probabilities and multiply them all because of the independence, then it has to be p cubed q to the 4. This one is more because there's more than one way this can happen. There's lots of different orders, different things the monkey could have typed that would have gotten exactly 3 s's. This is all review from last class. Any questions or comments about that one? Yeah. Yeah. Well, in question 2, I think the order, I would say the order does not matter in question 1 as long as there's 3 s's. There could be 3 s's, but they could come at the beginning, they could come at the end, they could come at the middle, they could be all spread out. That's why in question 1, you have this extra factor of 7 choose 3. There's lots of different ways it could happen. In question 2, there's exactly one outcome that we're talking about. Like imagine taking the piece of paper that the monkey printed on. There's only one piece of paper that works in question 2. In question 1, there are 7 choose 3 pieces of papers that would be like, yeah, it happened. 7 choose 3, what is 7 choose 3 these days? Approximately 35. 7 times 5, yes, okay, very good. So there's 35 pieces of paper that the monkey could have come up with, and we would have been like, yes, the thing happened in question 1, but in question 2, there's only one. That's the difference. Very good thing to keep in your brain. Okay, what on earth does it have to do with this thing that I brought today? Ow, don't poke those things. So this thing, yes.
I have to ask you.
Yes, please.
You mentioned a real monkey just bangs on keys.
That's right. Well, apparently they also get bored. They will eat the typewriter and stuff. They'll
but
do
if
all
I
sorts.
was a monkey, which is pretty close to the truth, I am a primate, I think I would sit at the keyboard and go rocking back and forth like this.
Yes, that's a good hypothesis.
Would that change the probability?
I mean, yes. Well, yeah, because then this would be very likely, right? This would be way more likely. The FSFS.
Way more likely.
But it is interesting. I would also guess that monkeys would do that because that's kind of what humans do, like babies. We'll do back and forth.
Back and forth, back and forth.
But no, monkeys apparently just slam the one button over and over.
No, I think we got
This.
a census of monkeys.
Okay, well, should we get next class? We're gonna bring a monkey into class, and then we'll try it. Okay, very good. So the question now is, what on earth does it have to do with this thing? What does it have to do with this thing? This is the Plinko game from The Price is Right. You take these little pink discs and you put them in the top, and they go ding, 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 and they kind of bounce around, and they end up somewhere random, sometimes on the floor. If the angle is not quite right, let's try that. And they end up in the middle. What does this have to do with the monkey at the typewriter? How is this like the monkey? So the claim I'm going to make, a very bold claim, is that the thing we are doing on the board, this binomial thing, is so general that not only does it apply for the monkey, but it also applies for this thing. You just have to know the right way to look at it. Does anyone have an idea? What is the similarity between the monkey and the Plinko board? Because at first glance, they look extremely different. Yeah. Yes, that's very good. So the first basic thing is that they are both about a random variable. So the number of s's is a number between 0 and 7, right? There could be 0 s's, there could be 1 s, there could be 2 s's. And the Plinko board, there are different outcomes. You could end up here on the far left. You could end up on 1 over, 1 over, 1 over, 1 over. So there's a bunch of different outcomes, and there's a bunch of different outcomes over here. That is saying both things are random variables, which is absolutely true. Not only are both things random variables, but I'm making the stronger claim that they are, in some sense, the same random variable. They're the same. There's something about the Plinko board that matches this thing with the monkeys. I will say one other thing. The monkey, remember, had 2 outcomes, S and F. monkey, 2 keys. If there were more than 2 keys, it wouldn't be a binomial distribution. It would be something called the multinomial distribution. Binomial means there are 2 outcomes for every individual thing. This board somehow has 2 outcomes baked into it. What are the 2 outcomes that live in the board? Yeah. Left or right, exactly right. So the similarity between the monkey and the board, the monkey is doing S or F, the board is doing left and right. And over again, this little pink puck has to decide, am I going to go left or am I going to go right? And because of the way it's made, each direction should be about equally likely, 50% likely either way. And this is the other thing. The monkey, we said, is doing it independently at random. To our best of our knowledge, the board also does it independently at random. So if you kind of know that it went right in the first level, that doesn't help you predict what will happen later on. So the monkey and the board are both doing the binomial distribution, where every level is left or right, or I guess the monkey will never do that. Every level is supposed to be left or right with equal probability and independently at random. One level does not affect the next level, so they will both satisfy this kind of math. That's what's exciting about the binomial. There's so many different real-life situations that match it. I'm going to write this down mathematically in 1 second. Let's do that. So what do I want to do? I want to take this window. I'm going to write down, this is the way I like to think about it, because I like to think of everything in terms of the random variables. So statisticians sometimes try to avoid writing down the random variables, but probabilists, people who do probability, love random variables. We write everything in terms of random variables. So here's my definition. The definition, a binomial random variable, with parameters n and p. So p is a number between 0 and 1. N is some natural number. If you don't know what these symbols mean, you can ignore them. You got n and p. It can be written, instead of is, I'll say can be written. So it's x, and we would write x is taken from a binomial distribution. We would write it like this, bin of np. Bin stands for binomial, and it is written as a sum of a bunch of different things. And I'm going to write the things with an I. I1 plus I2 plus ... plus In. So it is a sum of n things. And the n things, they can be whatever you want. This is the magic of the binomial. In real life experiments, you figure out what the n things are. For the monkey, it could have been the number of s's. So let's do some examples. Example 1, the monkey. Example 1. I'm gonna explain in more detail what the i's are in a second, but I think it's helpful to have the examples. In example 1, the monkey, the i's count the s's. So i's count the s's. And in particular, I1 is equal to is counting is the first letter, an S. I2 is the second letter, an S. Second letter, an S. The other example that equally well fits is the Plinko board. In the Plinko board, the i's count if you go left or right. So the i's count lefts and rights. Count left versus right, and you could just arbitrarily decide that it should count lefts. Left is better than right, right? The first direction is left. Let's say that, and I2 is the second direction is left. So anytime you can count something up, and you can write the thing you care about as a sum of those individual things, it will be this binomial distribution. It could be monkeys, it could be the Plinko. As long as you can figure out a way to think about it where you're adding up a bunch of different things, lefts and rights over here, it gives you your final position, and counting up the s's gives you the number of s's, then you will have a binomial distribution. So what are the little things that you have to be careful of? The things have to be independent, where each, let's say the i's are independent. The i's are independent. And each I is counting one individual thing. And each I is counting one individual event. These are called indicator random variables. I'm going to put AKA. So I actually stands for indicator random variable. So each I is either 0 or 1. And so I equals either 1 or 0. And it's 1 with probability P. And it's 0 with probability that we called Q, which was 1 minus P. So anytime you can write the thing you care about as a sum of individual pieces, and each individual piece is either 1 or 0, so either it went left or it went right, or you could say it was an S versus it was an F, then the final outcome will be a binomial, and you can write it like this, binomial NP. We worked out its distribution last class. So the distribution, I'll write that down in a second to remind us. Any questions or comments about this definition so far? Maybe I will highlight where the parameters come in, right? So that's an important thing to keep your eye on, right? We had N and P. We had N and P. What were the N and P? Well, the N is the number of the things you're adding up, and the P is the probability of each thing individually coming up. That was the P. Let's make that orange. So that's where the N and the P come up in this final thing. And the final random variable you get depends on the N and the P. So the number of letters that the monkey types depends on how many total letters they type and the probabilities of each letter. Where this pink thing ends up depends on the number of layers and also where, the probability of going left and right. You might think right now it's 50-50 by symmetry, but if I tilt it a little bit, maybe it's 60-40. Actually, I think this would be a lot. Let's figure out what happens if it does this. I think this one's going straight to the side. Actually, okay, 60-40 or something. And you can tilt the probability one way or the other. That is changing the p-value. Okay, that's the binomial random variable. We're going to say more about it in a second. We're also going to learn how to make the computer calculate things for you. But any questions or comments about the binomial? Yeah. Yeah, you. Yes, I can scroll down a little bit, of course. Yes. Was there a question over here? Maybe the same question. You good? Yeah. Okay, yes. I'm using the notation that you might have seen in sort of calculus class, where they'll write something like f of x, let's do it with a pen, f of x equals, and they'll say it's equal to 2x if x is bigger than 2, and it's equal to minus 7 if x is less than 2. This might be a problem in your calculus class. So this big curly bracket is saying there's two situations that can happen, and in my situation, the actual outcome is random, right? So sometimes it's equal to 1, and sometimes it's equal to 0, and I've told you the probability of these events. Yeah, fantastic question. I'm said it's probability P and probability Q for being 1 and 0. Yeah. Bin, yes, this is bin. Let me say this. We write this as this. So in other words, this definition, DEFN, means this is a definition, and this is defining what it means when someone writes bin. They mean all of the stuff that we just said. So when someone says this is a binomial random variable, or they write x is bin NP, this is exactly what they mean.
I think he's just wondering that that's abbreviation for binomial.
Yes. Bin is an abbreviation for binomial.
Yeah.
All right. This is important because I think you have a homework problem where it says find bin of question mark, question mark. You have to fill in the blanks, and you have to know what it means. All right. Other questions? Okay, and as a quick reminder, we worked out last class. This would be like a proposition. So proposition. The probability, I'll say it like this. If x is bin NP, then the probability that capital X equals lowercase x is equal to n choose x times p to the x times 1 minus p to the n minus x. This is what we worked out last time. So the proof is we worked it out last class. So in formal mathematics, we like to organize all our work into propositions, proofs, and definitions, examples, and this is how I would write out the result that we did last class. Okay. Any questions? Okay, and so in the homework that you have, normally the homeworks are due on Friday, but I made an oopsie and I didn't post it until Saturday, so I gave you guys a couple extra days. It'll be due on Monday, so a week from today. I just took the regular Friday and I added 24 business hours to it to get Monday night. And in that one, you're gonna have to work out some different random variables. You're gonna have to tell me what they are, things you care about. And you'll see that very often you care about events like, this is a remark, I guess, you often care about things like, you often want to calculate things like the probability that capital X is greater than 3, or the probability that X is less than 4, or maybe say less than or equal to 4. So on my Plinko board, you might be interested not in exactly where you end up, but you say, what's the probability I end up on the far right, the far 3? That's the kind of thing you might care about. And so the binomial random variable is a really nice example of a random variable where you can understand where it comes from and also write out different events. That'll be on your homework. CEG homework. Okay. Any questions or comments about the binomial? All right, let's see how we can make the computer do these kinds of calculations for us. So your homework, you're setting it up, and then in your next homework, you're going to be calculating these with the help of the computer, right?
Yep. That's
all right. Let's see it. We're going to learn how to use a little programming language called R, and some other more things about the binomial.
Okay, so we ended up with that slide last day. I noticed a couple things. I did a combination of a pre-post and a post of the last couple lecture slides, and then I put some pre-post for today, and we'll see where we get to there. Those are up there. I also noticed a couple screw-ups in dates I had posted, so I've fixed those up, and I just noticed those today, but hopefully that will help make some sense of what you've seen. I want to kind of emphasize, and you've been working on this right from the very start with the mathematized questions today, is the two pieces of this equation that we derived, and to just recognize again, make sure you understand what the two pieces are. The easy way I think of thinking about it is that this piece here gives you the probability of getting a particular sequence of X successes and N minus X failures. And then you really don't typically care what order they're in if you just want to say what is the probability of X successes in N trials. So then what this does is it counts the number of ways you can get X successes in trials. And there's various ways you can phrase that. One of the ways is the number of ways you can permute X successes and N minus X failures in those N trials. So just this basically works out all the different arrangements of getting X successes and N minus X failures, which are distinct. They all have the same probability, so we can just multiply those. So the binomial distribution to me has a great beauty to it in that, first of all, it's exceedingly important. It's one of the most important distributions in statistics. It has kind of a cool equation, but the point is we can derive it from first principles, from our basic principles of elementary probability combined with what we know about counting rules. Okay, so you have seen a simulation of the binomial distribution. This website here is an electronic form of this. You can play the quincunx here. So that's kind of a weird name, the quincunx. And that's what Professor Nika has here, is a quincunx.
So this is exactly what we did in real life, except the digital version. There is one actually very small difference between this one on the screen and the one in real life. That is actually important a little bit. Does anyone know what the difference between this one and the one in real life is? Yeah. No walls, yes. So the one that we have in real life has these walls, and that's because it has so many layers that if you wanted to include all the possible outcomes, it would have to be extremely wide. So the people who made it sort of cheated and added the walls. You can fix that up in the math by applying some function to X or something. But this one over here has no walls. So this one is the pure math. And again, it's the idea that every single ball chooses to go either left or right. And the lefts and the rights are the things we're counting to make it a binomial. The fun thing is you can also change the size and the speed. Let's
change the speed.
The speed. Well, let's make it big first.
I want to go fast.
I want to go big. We'll go big and fast. Do I have to restart it? Oh, a huge one. Okay. So there's a really big one. Maybe that's too big. Let's go down to 10. Geez, holy. Okay. But now the fun thing is we can speed it up and the balls will start dropping, and we will start to accumulate the number that ended up in each bin. And as you accumulate more and more, you will get closer and closer to the true probability distribution that we did over here. This kind of thing is sometimes called an empirical probability distribution. It's like you ran an experiment, how many of each outcome did you get? Versus the true probability distribution is the actual honest-to-God probability that we calculated. And we'll see that maybe we'll leave this running for the rest of the class, and we'll come back to it at the end and see what it's gotten to after we've dropped hundreds and hundreds of these Plinko balls. We're up to 130. Maybe by the end of the class, we'll be in the thousands.
I think it has a limit.
It has a limit. Okay, well, we're going to find out.
It has a limit.
We're going to find out if the website has a limit or not. Maybe we'll run out of internet.
Okay. So, couple notes to just kind of pay attention to. The random variable is a discrete random variable, and it can take on values 0, 1, 2, and so on, because we're counting the number of successes. We don't get 3.2 successes. We could get an average of 3.2 successes, but on any particular set of n trials, we have to come up with a non-negative integer value between 0 and n. So if we say how many values can x take on, don't know what that is. How many values can x take on? Yeah. How many would you say? What did you say? N? Do you like n? Everybody agree with n? Anybody disagree with n? Come on, I'm looking for a disagreement. Disagreement? Do you like n? You like n? You like n? Do you like n? You like n? I'm looking for some. First of all, n's wrong. So I don't want to see you all agreeing with that. What did you come out with? No. You've got, if you do 10 trials, could you have an infinite number of successes? No, you could only have up to 10, right? So how many different values could x take on if n equals 10? Go away. My car is ill. My car is ill. That's what they're trying to tell me. My car is ill. And it's going to cost me a fortune to fix. Okay. How many did you come up with in trials? How many different values can x take on?
Should we do a mathematize if people are unsure? Let's make a new little mathematize. So we're doing a binomial with n trials. How many different possible values could we get? Let's do a really quick mathematize here so we don't single anyone out. So mathematize. And we're going to do
They have terrible clips on these things.
how many different values is it possible that x could have? And I'll say when x is binomial NP. Okay, it is open. I have to put in a thing. Let's get a numerical answer. Oh, I don't want a numerical answer. Let's get a math answer. Okay, actually, let's choose some particular values. You said n is 10, Gary. Is that right?
Yeah, I took 10.
10. Okay. Suppose n equals 10. What is p? Maybe it depends on p. Let's make p a half. P equals 0.5. Okay. How many different ways can you do it? And it is open now. So tell me, how many different ways? It's a little bit.
Do you have to put that on the screen?
Oh, I have to put it on the screen. Okay. Let's put it on the screen. I think they can see it on their devices, but now it really is open. So if n equals 10, how many different values are possible? So this is like a monkey who's typing out 10 letters on the keyboard, and we're counting the number of S's, or maybe we're dropping the Plinko board with 10 layers. We're adding up 10 different lefts and rights. Where could we end up? Okay, maybe we'll give you just 30 more seconds for a quick opinion. Okay, 5 seconds left. Put in your final guesses. And let us see what people went with. Ooh, this will be exciting. Let's do it with the labels hidden to start. Okay, was there one? Ooh, there's 2 answers. One answer has 20, and one answer has 19. So people are pretty split. People are pretty split. Let's see what people actually said. Reveal the actual counts. And I have to zoom out or something to see it. The split is between 10 and 11. So some people think it's 10. Some people think it's 11. Very slight eking out of 10. 10 people think 10 is more common. 10 seems very tempting because
Well,
n
that
equals
wins
10.
the presidency.
Majority
vote.
Depends which country you live in. Yes. Depends how we divided the ridings of the room. Okay. But 10 is the majority or the plurality vote. Unfortunately, 10 is wrong. 10 is wrong. It is not 10. It is not 10. And I will reveal, in fact, that 11 is correct. So if you said 11, congratulations. Way to go against the crowd and still get the right answer. This is very confusing when you first see it. Why is it 11? You told me n equals 10. But remember, n is the number of the length of the sequence. So I like to think of the monkey. I'm a monkey at heart. 10 is the number of letters, but we're asking for the number of different values that x could have. And that is 11. Does anyone have a nice, simple explanation why it's off by 1? Yeah. You have to include 0. So it's very nice. So if you count the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's 10 different outcomes. But there is also the secret other outcome of having 0. And that adds 1 more. That's why it is 11 instead of 10. For the monkey, you could have 0 s's in the string. You could have all the way up to 10 s's in the string. And that's why it is 11. I guess if we go back to the board over here, the binomial distribution, x can take on the values starting at 0, because you could have 0 successes, or you could have all the way up to n successes, and that extra 0 means there's n plus 1, not just n. Very good moment. Okay, we stumped half the class. That's good. That means half the class is learning something. The other half is already new.
Well,
I figured it out.
It's tough to be like fresh on a Monday morning. Like,
Yeah, that's
let's
true.
face it.
That's true.
I would say
Yeah,
those
do we
that
get
are
any-
stumped, it's like, we're still like trying to wake up for the day,
Yes.
for the week. So it's not a problem. Okay. Okay. Next little thing, we'll just put this in for now. The expected value mean of x is n times p. Now, Professor Nika is going to, in the future, discuss more on expected value. I'll discuss more on expected value. But let's just think about it from an intuitive perspective, okay? We flip a coin 10 times, it's a fair coin. We say, on average, how many heads will I get? Well, you're going to expect to get 5 heads and 5 tails if it's p equals 0.5. But let's suppose the probability of getting a head was only 0.4. And you flip it 10 times. Well, n times p would be 4. Well, that kind of makes sense. If the probability of getting a head is 0.4, we flip it 10 times. We would expect to get 4 heads. If we roll a fair die 600 times and say, how many times do we expect to get a 3 up? Well, the probability of getting a 3 is 1 out of 6. And there's a 5 out of 6 probability we don't get a 3. But 600 times 1/6 would be 100. Does that make sense? Well, you roll it 600 times, we would expect it to come out with each face equally often. And so, yes, the expected value, the average number of times we would get a 3, we'd expect it to be 100, right? 600 rolls, 1/6 probability of a 3 on each roll. Okay, so that's a quick intuitive sense of the idea of expected value, and we will be going over expected value in more detail. And I haven't put the variance up, but that can stay for another day. That's another day.
So if you're interested in this expected value thing, we are going to do it in more detail later. It will be a bigger part of the course later. But it is also introduced in that introduction video that you saw, the recorded video right at the end. They were calculating the expected value. So if you want to recap or you're interested to see why, there's a nice little argument there. It wasn't presented as the binomial distribution there, but it is the binomial distribution in fact. So now that you know that, you can go back and use your secret knowledge. Okay.
Well, we've discussed this. We derived it. We've got that. But the next thing is going to be the idea that computer software makes it very easy to calculate binomial probabilities for specified values of n and p. Well, when I say for specified values, it's for whatever values of n and p you specify. Okay, so we got various ways to calculate this, but this is the message I want to leave today, is to install R on your computer. Okay, and I'm not going to write out how to install R, and we're going to show you how to install R on your computer. Has anybody got R installed on their computer? A couple of you have, a few, but a very small number. So let's just take a look at installing R on your computer. And I'll say a couple words about R. Let's see, now am I going to cause myself grief by escaping there? Probably, but I'm going to try to go to the internet. I am going to try to go to the internet. And I've, oops, just a sec. Okay, we got that. Here I am. And now I am going to Google the letter R. The letter R. Now it's going to probably say, oh no, you want Raptors Republic, because I must admit I am a Toronto Raptors fan. But no, I'm not. I just want to Google the letter R. And what comes up first is the R project for statistical computing, okay? So that's the first thing, is if you don't want to just Google the letter R, you can Google R project for statistical computing. And here's what I want to emphasize about this. You will use this, we will use this extensively in almost all of the other statistics courses you take at this university, okay? And it's got various advantages to it. You can use it as a basic calculator, but then there's all kinds of functions pre-programmed for you. And then there's all these packages that do much more sophisticated statistical analyses. The other thing I will mention about R, it is free to everyone in the world at any time. So it is not proprietary software. And it gets updated by this kind of like team of volunteers, and it's kind of a giant collaborative project around the world, okay? And I'm convinced it will always stay free. The basic R, we're going to discuss R Studio in a little bit, but not right now. Anyhow, if we go to the R project for statistical computing, this is an enormous website, okay? And what I encourage you to do is never get intimidated by really large websites, really large amounts of information. Kind of glance at them and say, you know, what can I harvest right now that gives me an overview that I will find potentially useful in the future. So they will then got this getting started. And it runs on Windows, it runs on Macs, it runs on Unix platforms if you are into Unix, which some of you probably are. And then to download R, it'll say, please choose your preferred CRAN mirror. Okay, so if we go to download R, then it's going to come up to a thing is, where would you like to download it from? Well, we're in Canada. And it honestly doesn't matter where you download it from, but I typically download from University of Waterloo. So that's all there is to that. And I'm not going to go through because I've installed this myself on it, but it'll go through, it'll download a file that you execute, and you can get the icon put up on your screen. And well, it installs very quickly. Now I'm going to mention one other thing is some of you will have heard of something called R Studio. So a lot of students prefer to work with R Studio rather than base R. There's reasons that in intro statistics we typically stick with base R. R Studio is very nice. My issue with R Studio is it is proprietary software. They make a certain version available to everybody for free, at least for the time being, with various upgrade packages that you can pay for. It does have some advantages. if you wish, which I kind of encourage actually, is download both the Base R and RStudio, okay? But when I do things, I will generally be working with Base R. I should mention that RStudio is simply a wrapper around Base R. It's powered by Base R, and then it's got some nice features for wrapping up Base R. Okay, so I think that's what I wanted to say about those things. You'll get that, and let me see. Let's see if I go to the mirror, and then you'll see. Yes, you pick your mirror, and then it will say, do you want to use Linux, a Mac, or Windows? And once you pick, I have a Windows, but that's because I don't have a Mac. You have a Mac, don't you?
Well, I think the statement I have Windows because I don't have Mac is false because there's also Linux.
Yeah. Oh, you have Linux too. Well,
Wow.
yeah, you do it all.
You need a knot of two, a knot of an or. Okay, anyway.
Okay. Anyhow, you'll see the install R for the first time, and everybody gets that installed very readily. And let us know if you got a problem on that. We also have an R help lab, which can help you if you have a problem. I'll get you information on the R help lab. I actually don't have that with me right at the moment. Okay.
So once again, the main reason you want to install R is because you use it in all the stats courses. So you take
We use
20,
it
2040, 2050.
We use it
all
on
the other
all
ones.
the stats
Okay.
courses, yeah.
Worth your time to install it.
Yeah.
All right.
And
what does it look like?
What does it look like? Well,
I'm dying of anticipation.
You're dying of anticipation. Okay, so let's see if we got. Let's just do down. So one of the things you'll notice, I got all kinds of R versions up there. There's reasons why I hold on to old versions, but every so often you download the new version, and this is the current new version, the newest version, at least it was as of a week ago. And that's what it looks like. And you see, you can use it as a very basic calculator. And there's lots of other things we can do with this. We're not going to go through a learning exercise in using R. There's all kinds of tutorials on getting started on R and this kind of thing. But we'll get you going pretty quick on doing some basic things with R. So let's think about the basic things we want to do with R. Oh my goodness, how many things can we do? Well, okay. So we're going to use R to calculate some binomial probabilities. We're also going to use it to perform some simulations, and the simulations where it gets really quite cool. And let me just bring that up for the current thing. Where are we here? What do we got? We're almost at 20 after. I can't.
We could do one of these.
We can do one of these?
So we have a monkey has typing 10 letters, and they have 50% chance for each. Let's do the probability x equals 4. I want to do the probability x equals 4.
Okay.
That's almost the warm-up problem.
Okay. So we actually need to show another slide before.
There's not just some quick command like
there's a quick command,
and it just does the abracadabra 10-4.
Well, you know what?
0.5.
I'm going to bring up a couple points because the last minute I don't want to be pushing over time. I'm going to have to push this.
Sleep tonight,
but I know. So let's make sure that they have something to help them go to sleep.
Oh, all right.
Or actually, it'll probably keep them awake. So one of the things, there are online calculators. This is one of them. That has annoying ads that pop up. Okay, StatTrek. It's kind of a cool name. We can look at StatTrek. And we're going to do that next day if you want to take a look ahead on it. Easy to work with.
So this is what it looks like. And if you type in the right number of things, it'll give you different things. So I guess we did 0.5, 0.5. Number of trials we said was 10. And then we're looking at 4. X equals 4. And we hit calculate. And look, it calculates a whole bunch of stuff for you. It sort of automatically does the calculations. And then your job as the human is to interpret in the context of the problem, which will be on
This is very
homework
cool.
in the future.
Yes. That will be it for today.
All right. Perfect.
Yes. Time has run out. Trouble is the discussions of these functions take a little bit of time.
Hey.